All right, so here we are over in the notebook that we finished up in previously. So I've just got a new code cell down here, and we're going to get our example code in here. So the first thing I want to do is define sigma x, sigma y, and tau xy. And we said theta, our initial angle, theta, we'll say theta subscript d for degrees was a negative 35. And then if I want to calculate that in radians, I'm going to multiply by pi over 180. So I'll say theta d times math.pi over 180. All right, so the first thing I'm going to calculate the stresses on an element orientated at theta degrees. So I've just said theta here because that could be a variable. I can change this angle. Once I write this code, I want to write it in such a way that I could change any of these numbers up here, and obviously everything would update itself. So I don't want to hard code in negative 35 there. All right, we have seen this before. So all I'm doing here is rewriting the transformation equation. So in fact, let's save ourselves a little bit of heartache and just copy that in there. Okay, we've seen that further up. All that is my transformation equation, and obviously it's taking in sigma x, sigma y, theta, and tau xy. So that should work straight off the bat. Let us just throw in some print statements here. One I prepared earlier. So what have we got? We have a print statement here that just says the stresses on planes orientated at, let's say, x degrees to the xy axis, and then we let x, in this case 1, equal to theta d. And then I'm just printing out sigma x1, sigma y1, and tau xy. Let's run that and see what we get. And excellent, we get exactly the numbers that we'd expect. 9.7 in compression for x, 14.6 in compression for y, and 22.5 for the shear stress. All right, so far so good. Let's move on and calculate our principal planes. Okay, so the first one, let's say theta 1 is going to be, and we'll just put in the equation that we had previously, so 0.5 times math.atan, so tan inverse. So this is going to be tan inverse of something over something else. All right, the numerator is going to be 2 times the tau xy, and the denominator is sigma x minus sigma y. So then I'll say theta 2 is going to be theta 1 plus 90 degrees, and 90 degrees in radians is math.pi over 2. All right, and now I just want to get those two angles in degrees. So let me say theta 1d is going to be theta 1 times 180 over pi. So those are both of my principal angles in degrees, right? So let's go and print those guys out. And again, I'll copy in some print statements from my little cheat sheet over here. Right, so we've got principal angles. Principal angles are variable 1 and then variable 2, and then we pass in the values. Let's print that and see what we get. 13.1 and 103.1 degrees. Excellent, exactly what we saw when we did this out by hand. Now let's work out our principal stresses. Now, as I said, we could work out these principal stresses completely independently, and we wouldn't initially know which principal stress was tied to which angle. And so the easiest way to do this is to just feed those angles back into our transformation equations, and then the corresponding principal stress will drop out. So I'll just say sigma 1. Now, I don't yet know that sigma 1 is actually the largest or the major principal stress. I'm just speculating at the minute. We'll do a little if condition to test this now in a second. So feeding into my transformation equation, let me see, can I be clever about this? Can I copy? Let me copy all of that. Throw it in there. And what am I going to have to change? I'm going to have to change that theta to theta 1. And this needs to be theta 1. Everything else should be okay. And then I should be able to do the same thing for my second principal stress. I just pass in a different angle, theta 2 and theta 2, and that should be okay. Let's print these guys out and make sure they're the numbers we expect them to be. Excellent, and that does agree with what we said. Now, I plugged in theta 1 here, theta 1, and that gave me a negative 34.8 for sigma 1. Now I actually know sigma 1 happens to be this guy down here. Okay, so I was speculating, I was just calling this sigma 1 and this sigma 2, but I didn't actually know whether this was going to be the algebraically largest one, and therefore this would be the smallest one, and it turns out that that's not the case. And so I'm going to want to write my code, as I said, in a way that allows me to change all of my input variables here, and I don't want to have to then manually go down through this and do a manual check to make sure that sigma 1 that got calculated was my larger of the two stresses. So this is a perfect example where we can use a little if condition. So I'm going to say if sigma 1 is greater than sigma 2, so if sigma 1 is greater than sigma 2, what do I want to do? Well, I want to print a set of statements, and it's going to be these guys here. So if sigma 1 is greater than sigma 2, well then it means I would have guessed right up here, and we can report this. We can report the line sigma 1 is whatever, and theta p1 is whatever, and then I pass in values for those 1 and 2 variables as sigma 1 and sigma 2. Now, Otherwise, I need to swap them around, don't I? Which is the case that we're in here. Okay, so otherwise, and I'm just printing a little space out here at the end. But otherwise, we're going to say sigma 1 needs to be actually sigma 2, and theta p1 happens to be theta 2 essentially. So now, if I run this, what you'll see a little set of statements here, which is these last two statements, which you'll notice in these two statements actually, I haven't actually said, I've just said the principal stress, this guy, occurs on this plane. And then I've said the principal stress 10.5 occurs on this plane, right? I've not actually said in those two statements which one is sigma 1 and which one is sigma 2. For that, I needed to use my little if condition here. Once my if condition has executed and done my test for me, now I'm in a position to say, okay, well, sigma 1, okay, the major principal stress, which is always sigma 1, that's 10.5, and that occurs on a plane of 103 degrees. And sigma 2, which is always my algebraically smallest principal stress, is going to be this guy here, right, which is going to be occurring on a plane orientated at 13 degrees. Next, we can work out the planes of maximum positive and negative shear stress. Right, now I need to know which one is sigma 1 and which one is sigma 2. So my little if condition up here, all it did was it printed a couple of statements. It didn't actually define any new data. And so I'm going to repeat that if condition again. I don't have to repeat it. I could have just put the logic I'm about to put in this following if condition. I could have put it in here as well, but I've decided to keep it separate just for clarity. So we'll say theta S1, because I'm trying to work out these angles for the planes on which the maximum shear stresses occur. But remember, we defined those relative to theta P1. So we said theta S1 was theta P1 minus 45 degrees. So, I need to know which one is theta S, or which one is theta P1. So if sigma 1 is greater than sigma 2, well then that means the theta S1 is equal to theta 1D minus 45, right? So that's the plane for the maximum positive shear stress. Let's just put that in. Else, theta S1 is going to need to be defined as theta 2D minus 45. Okay, and once we've got theta S1, well then theta S2 turns out to be theta S1 plus 90. Okay, so this is the plane of the maximum negative shear stress. All right, so this, as I say, this little if condition, all this was doing was making sure we assigned the correct value to sigma S1. Okay, because we did it up here, but all we did here was within this if condition up here was print out a couple of statements. But here we need to do the exact same test, but within this test we're actually defining theta S1, because you'll notice the thing that differs between this if condition and this if condition is which value of theta P we're defining as theta P1. All right. Okay, so now that we have those angles, we can go ahead and give ourselves another little print statement. Right, so we're saying the planes of maximum positive and negative shear stress are, and then we're just printing them out.
All right, so what do we have? The plane of max positive shear stress occurs on a plane of 58.1 degrees. Yep. And the max negative shear stress occurs on a plane of 148 degrees, which is correct. All right, now we can just go ahead and work out what is the maximum shear stress. Okay, so we can say that tau max is going to be equal to 0.5 times sigma 2 minus sigma 1. And because it's just the magnitude that we're after, we can just take the absolute value, right? So the positive version of this number. And then the normal stress that exists on those planes, we'll just call it sigma underscore s for shear. i.e. it's occurring on a shearing max shear plane. Well, that's going to be 0.5 why am I not doing that right? 0.5 times sigma x plus sigma y, the average stress. Now let's drop in a couple of print statements. So let's run that and see what we get. Okay, very good. Now, the maximum shear stress has a magnitude of 22.7 newtons per millimeter squared. We know that's correct. And the normal stress that is on the max shear stress planes is negative 12.2. So at 12.2 newton per millimeter squared compressive stress. Right, let's go ahead and do some plotting here. So we're going to be repeating a lot of what we've done already. So I'm going to, where possible, copy in some code. So what am I defining here? I'm just defining a range of angles. I'm just using a capital T for my theta this time, just to differentiate from anywhere else I might have used theta up here. So we've got a capital T for my theta. Now we've got our transformation equations. Let's just drop those guys in. Again, we've seen this above, and I'm just defining all of the values that are created by this transformation equation with a sigma x1 with a capital S here. Again, just to differentiate from above, capital S and capital T. We can go ahead and plot those. Right, same thing, defining a figure. I am adding a set of axes, and then I am just adding a plot. I'm plotting the sigma x1, sigma y1, and tau x1, y1. Now, what else can I do? I can drop in my little housekeeping code at the bottom. Right, this is just adding the x label, y label, title, x limit, x ticks, legend, and I think I'm also going to want to have plt.grid. I'd like a grid to be turned on. All right, let's see what that gives us. Boom, 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 boom. Excellent. All right, so these are the plots of our transformation equations. We've seen those similarly above. Now let's start plotting on some values. So I want to plot the stresses at 35 degrees. Right, so I'm going to bring in a sort of line by line here. So after I've plotted my transformation equations, what do I want? I'm going to come along and I want to plot. Let me just bring the code in. The reason I'm not typing this out is because I'm bound to make a mistake. So what have I got here? I've got axes.plot, and I'm plotting a vertical guideline at 35 degrees. That should be negative 35 degrees. Right, so I've got theta d, and then they're my x coordinates, and my y coordinates are just going to be the maximum values of stress, normal stress. All right, let's run that. Okay, so there is my vertical line, and then where that line is cutting these curves are the stresses that we worked out in the very first part. So the shear stress, the stress sigma x1, and then the stress sigma y1. So now let's go ahead and plot some markers. Let's plot a marker on this thing. What do I mean by plot a marker? I want to plot a dot on this graph, somewhere on this graph, at the exact point that I calculated the stress sigma x1 to be. Right, so what does that mean? Here we go. So I'm saying plot. Now I'm just plotting a single data point this time, not a line. So my x coordinates is just going to be one number, and that's going to be theta d minus 35 degrees. And then the y coordinate is going to be sigma x1, what I calculated sigma x1 to be. I'm going to plot that as just a sort of a circular marker. Its color is going to be lime, and its marker size, I'm specifying it as 5. Let's run that. Okay, so there you have it. You can see that the point that we have calculated to be sigma x1, right? It turns out, of course it turns out, that it lines up exactly on our plot here for sigma x1. All right, now what else are we doing? Let's plot sigma y1. Take this, copy it, and this time we'll have sigma y1, and we'll call that sigma y1. And while we're at it, let's just in one hit plot tau x1 y1. Tau x1 y1. Right, run that. Excellent. All right, and I mean, look, there's no surprises here. We calculated these numbers already. All we're doing is saying wherever I drop that vertical dashed red line, wherever it cuts these three different curves, those are the values for the corresponding stresses at that orientation, that negative 35 degrees. And so it's expected that we would have our dots lining up on the curves. All right, let us go ahead and do another little bit of plotting now. Let's plot on our principal stresses and principal planes. Come down here and say plot principal stresses and planes. Right, so what am I doing now? So I'm saying I'm plotting a line, a vertical guideline for the principal stress sigma 2, the smaller one, right? So we know that that occurs at theta 1d, right? That's the angle at which it occurs. And so this is our vertical line. Excellent. That's this red vertical line here. And straight away we look at that and we say to ourselves, ah, perfect. It is a vertical line that is at the point of the maximum, the major principal stress, sigma y1, right? And we said that was 10 point something. And then the minor principal stress, which was a negative 30 something, whatever we said it was, negative 34.8. And so that makes sense to us that the line is happening right here at the peak of this and the peak of this. What will we do next? Let's plot a vertical line, another vertical line. So this time we're plotting a vertical guideline for the principal stress sigma 1. Okay, so this happens to be the larger principal stress. Okay, so that's another 90 degrees out to the right. And so that was your, what did we say that was? 103 degrees. Okay, so that's that vertical line there. Now let's plot a couple of markers for those stresses. So the next plot here is going to be a single data point. It's going to be located at theta 1d and sigma 1, right? So this happens to be, in our case, our smaller principal stress. It's going to be a line dot. Let's see, and there we have it there. Okay, so that's the smaller of our two principal stresses. And we can go ahead and plot the larger or the major principal stress. So this is going to be theta 2d and sigma 2. And we'll plot that guy. And there we have it there. All right, so we're nearly there. I'm going to make this a little bit easier, I'm going to hide that and I'm going to hide that just because it's starting to get a little bit clogged up now. So now we can go ahead and just plot some shears. Right, so plot the maximum positive and negative shear stresses. So what's the first one I want to plot? I'm going to plot a vertical guideline for the maximum positive shear stress. So it's a vertical line, so its x coordinates are the same, and they're going to be at theta s1. And then I just want to plot from a negative tau max to a positive tau max. It's going to be a red dashed line again. And there you have it. There's our red dashed line. Okay, and let's plot another dashed line for the maximum negative shear stress. Okay, and there we have it there. There's your dashed line for your maximum negative shear stress, and this is the dashed line for your maximum positive shear stress. So let's go ahead now and actually plot them. Right, so I'm plotting a single data point for theta s1, so its x coordinate is theta s1, its y coordinate is tau max, so this is the maximum positive shear stress. And we're also doing the maximum negative shear stress at theta s2. And let's plot those, and sure enough, there you have it. There is theta s1, or the maximum positive shear stress theta s1 at theta s1, which was 58.1 degrees, and the maximum negative shear stress, look, it was supposed to be at 148.1 degrees, and sure enough, there it is at 148.1 degrees, and it is the negative 22.7 newtons per millimeter squared. And while we're at it, we might as well go ahead and plot the normal stresses that occur on those planes with a couple of data points. So I'm plotting theta s1, the x coordinates theta s1, and the stress is going to be sigma s. So let's just plot those. And in fact, just to make it a little bit clearer, we're going to we're going to get rid of those. So we only have our 2 line points, and there you have it. Look, the 2 stresses we worked out to be the value of the normal stresses on those planes of maximum positive and negative shear stress. There you have your line dot there, and your line dot there of minus, what was it, 12.2 newtons per millimeter squared. All right, so not all of this was strictly necessary. I mean, once we had worked out the values of these stresses and all these angles over in our handwritten notebook, we more or less had the problem solved. At this point, all I wanted to do was make that link between all of the values we've been working out up until now and where they appear on these plots of our transformation equations, just to kind of reinforce the link between the transformation equations and the principal stresses and the maximum positive and negative shear stresses. All right, so that is it. That's about as complicated as it gets. I'll put it a different way. It doesn't get really any more. There's no more to it than that, really. What we're going to do in the next lecture is we're going to take everything we've learned so far about 2D stress analysis, and we're going to look at an alternative representation, or an alternative way of thinking about it, and it is in the context of something called Mohr's circle. And once you wrap your head around Mohr's circle, I've been building this Mohr circle up now over the last few videos as this great thing. But once you wrap your head around this Mohr circle, you're going to see the complexity. If you do see these as complex problems, you're going to see that complexity melt away, because Mohr's circle makes this a very intuitive and relatively easy to solve. Any of these problems relatively easy to solve. Right, take a break. We're coming back for the last video on Mohr's circle, where we're basically going to tackle this exact question, and we're going to look at it in the context of Mohr's circle. So we'll come back and pick that up in the next video.